Okay. And then kind of similar to what we saw in the when we were dealing with linear kinetic energy, or when we were dealing with the change in kinetic energy for linear systems, we can model the work done by rotational systems as the change in kinetic energy because we know that this equation is going to give us the kinetic energy for angular systems. Okay. So in this case, we also have an equation for angular momentum. So for angular momentum, we have this equation here, where we kind of talked about this previously, but if we have a rigid body, okay, and it's rotating about this axis, so we need the total ICM, right? And then just the angular velocity, okay? So this is going to give us our momentum for the system, our angular momentum, and we can use those, and we can actually relate we'll talk about this a little bit later, but if we also have like a linear velocity coming off of or tangent to how something's rotating, we can use collisions and these the linear momentum for systems. Okay. And then one last thing here. So we know that torque is actually equal to the change in angular momentum over the change in time. There's one homework problem that this will actually be, so we can also model this as delta L over delta T, right? Because a derivative is basically just like a change with respect to time. So I think there's one problem in your homework where they give you this, I think it's number 3, right? Where they just give you, they want you to find the torque and then they give you angular momentum and they give you time. So you can model it this way, right? Where if I know the change, if I know how much it's changed, and I know how long it took it to change, like the change in time, then I can use both of these to solve for torque. Okay. All right. So we're up to our first problem. So I'm going to go ahead and stop this and then jump into the first problem.